Hi, in this video we will consider implementing a software algorithm on a heterogeneous computing platform using Protoip. The algorithm of interest is the following. We have two inputs, vector x of 10 elements and vector alpha with 2 elements, and two outputs, y1 and y2. These are two vectors, 10 elements each. And we want to perform the following calculations. So firstly we calculate sine of alpha, firstly sine of first element alpha, and then multiply this scalar by a vector of 10 elements. And we do the same thing for the second element of vector alpha, and we multiply this scalar with vector x in order to get y2. And our goal is to split this computational workload between CPU and FPGA. So this is what we call heterogeneous implementation, and we will do this splitting in the following way. So we will put calculating sine on CPU, and then we will accelerate scalar vector product on FPGA. The reason why we do this is because sine operation is not well mapped on FPGA. In other words, sine operation requires a lot more resources compared to other operations like addition or multiplication. So, considering interfaces, we have two input vectors and two output vectors for our SoC. And in addition to that, we specify some interfaces for CPU and FPGA communication. And for this example, we send a coefficient, which is sine of alpha, and we send a vector, which is vector x for our example. And FPGA will accelerate this coefficient multiplication of coefficient by a vector and send the resulting vector back to CPU. Okay, now we'll go to Protoip project. The initial setup is the following. I have a MATLAB script. I will open that script, and here I have a set of commands, and I will be uncommenting these commands line by one in order to go through all the stages of the design flow. Before starting the design process, we will go through the steps of the design flow. So firstly we will create a template, and calling this make template command will generate C or C++ template, so template for FPGA as well as template for CPU. Firstly, we'll go through this branch of the design flow, and then we'll come back and do similar steps of the design flow for CPU part. The dashed rectangle highlights the blocks that are used only for heterogeneous implementation, while other blocks are used both for pure FPGA and heterogeneous implementations. Okay, so the first step is to call make template command. We go to MATLAB command line in order to call make template command. Before doing that, we will go through the list of interfaces again. So this is our system, and we will implement this structure by calling make template command. This command has a set of arguments. So firstly, we specify the type of template. There are two types supported by Protoip: PL, programmable logic, which implies that the whole code goes to FPGA, and another type is SoC, and we use SoC template for this particular application because we are incorporating both CPU and FPGA. We define the project name, okay, and then we have a list of interfaces that we use for algorithm implementation. We have four interfaces types: input, output, SoC input, and SoC output. So input and output corresponds to input and output to FPGA. So we see the list of input interfaces, vec in and coefficient. Okay, and we have one output, which is vec out. And also on the SoC level, we have two interfaces, two types of interfaces: SoC input, which means input to our system on a chip. We have X and alpha. Here we also have X and alpha, and we have SoC output. We have Y1 and Y2. Okay. Now everything is ready to call make template command. I call this command, and I get a report. In this report I can see the list of input, output, SoC input and SoC output vectors. The same list can be found inside our Protoip project folder. So here we have four folders in addition to the initial MATLAB script. So in doc folder we can find documentation for our project, including interfaces types, and some other project parameters. Okay. Apart from doc folder, we have IP design folder, which is Vivado HLS project and some source files from Protoip. IP Prototype is Vivado project, which incorporates CPU and FPGA. And in SoC Prototype folder, we have Xilinx SDK project and some source files that define the behavior of CPU. Okay, we'll start designing our system on a chip from hardware part, from FPGA part, and as I mentioned, FPGA is responsible for accelerating scalar vector product for this algorithm. What we do, we go to IP design folder, source, and we call we modify fooUser.cpp file in order to achieve desired behavior. So I will delete automatically generated code and write our own code for this particular algorithm. So the first thing I do, I define a counter. Then I have to go through the list of interfaces. So I have vector in, coefficient in, and vector out. And I will create a loop in order to perform scalar vector multiplication. We start from 0. We go up to the length of our vectors. Note that input and output vectors, they have the same length. So I could have chosen this code as well. We iterate over all elements, and in the loop we perform multiplication. We multiply scalar by a vector. So coefficient vector is a vector with one element. Essentially it is a scalar, and we choose the only the zeroth element. Okay, so we multiply input vector by coefficient and we get output vector. So this code seems to be correct. I will save it, and now we are ready to call IP design function. So what we do, we have generated code, we have added some user code to that code, and now we call IP design build function in order to transform high-level C or C++ code into lower level hardware description language code. And we do this by commenting the first command and uncommenting the command of interest. And I call IP design build. Okay, now IP design build command has finished execution. We can see a report here. And the next stage of the design flow, let's come back to the diagram. The next step of the design flow will be converting this hardware description language code into FPGA circuit bitstream that can be uploaded on the actual hardware. Okay, as we see, we do this conversion by calling IP prototype build command. Okay, this command has two arguments. We specify project name, as it was the case for all previously used commands, and in addition to that, we use board name argument, and in this case I use Z-board evaluation platform, so I specify the name of the Z-board. Now everything is ready to call this function, and I call IP prototype build. IP prototype build command has finished execution, and we see a report saying that FPGA prototype is built successfully. We come back to the design flow diagram, and now we have FPGA circuit bitstream. So now we have two possibilities. We can now we can test this FPGA circuit using IP prototype load and IP prototype test commands, and we will get some FPGA hill test results. Okay, we will not do this at this stage for time being. However, it is possible to do this to verify correctness. We will go directly to SoC design flow. So now we have FPGA bitstream, and in order to create an SoC, there is one missing part, is C code for CPU. So once we have FPGA circuit and C code for CPU, we can connect these two parts together and upload everything on the evaluation board. So this is the design flow that we will follow. Okay, and the next step is modifying users C and or C or C++ code that will go to CPU. Okay, I go back to Protoip project. I go to SoC prototype SRC source, and I have a set of automatically generated files, and the main files of interest are socuser.c and socuser.h. So we have some template code inside this file, and one option to modify this file is using your favorite text editor, and another option that Protoip provides is using debug mode in order to modify this file directly using Xilinx SDK software. And we will follow the second option. So I close this text file, and I will use SoC prototype load debug command in order to modify users C or C++ code. However, before calling this command, we have to call SoC prototype load in order to create this Xilinx project. So this will create Xilinx project and use template C code in order to build this project. Okay, and the arguments for this function are project name, board name, as it was the case for IP prototype build command, and we also define the type of interface that we want to use for data exchange. So this interface is the interface between uh, desktop machine desktop machine and SoC. So there are two options, UDP and TCP. I use UDP protocol, and we call this SoC prototype load function. Okay, now SoC prototype load command has finished execution, and now we are ready to call corresponding debug command, SoC prototype load debug. I run the script, and this command will open Xilinx SDK project that can be manually managed by user. So this is the Xilinx SDK project. In this workspace we have three projects, and the project of interest is test FPGA. We go to test FPGA project, and we have a set of source files inside this project, and there are two files that are supposed to be modified or accessed by user, socuser.c and socuser.h. Okay, we go to socuser.c, and here we have a function with a set of interfaces and some code generated by Protoip. Firstly, we go through the list of vectors, interface vectors. We have our X vector, uh, then we have alpha. These two are input vectors, so we have SoC X in and SoC alpha in. And in addition to that, we have two output vectors, SoC Y1 out and SoC Y2 out. And we can verify that dimensions are correct. So 10 elements in the output vectors, and in the input vectors we have 10 elements for X vector and 2 elements for alpha. Okay, now we should modify this code according to our algorithm. I will just copy paste it from the file, from the text file here. Okay, I copy and paste it here, and now we will go through all the lines of this code. I think it will be better to keep uh, the algorithm on the screen. I will open the algorithm. Okay, here it is. So in this code, the first thing we do, we define a variable that will store intermediate result of sign calculation. So we calculate sign of alpha 1, and then we will store this result in this sign alpha variable. The reason why I choose vector of one element instead of just variable is because Protoip is designed to deal with vectors, and whenever we want to use a variable in the interface, here or here in the interface, we have to define it as a vector of one element. Okay, so we put the result of sign calculation into this temporary variable. Okay, so we calculate sign of the first element of alpha. So in C and C++, we count elements of the array starting from 0. That is why I have 0 here. So I calculate this sign operation, and the next step is to send this result and vector x to FPGA. So what we do here, we send this data to DDR, where it can be accessed by FPGA. So we sent x vector. So we send this x vector to FPGA, this one, and then we send coefficient, which is just the result of calculating sine of alpha, and we send this coefficient here. Okay, so we send two vectors, and now we can uh, start execution, and we call start full function, which in this case has three arguments. All of them are equal to 1. Three arguments means we have three interfaces, so two input and one output interface, and all of them are involved in these computations. So that is why all these three arguments are equal to 1. So in the case when some of the interfaces are not used, we set them equal to 0, and the sequence of interfaces can be found in SoC user.h file. So we have definition of SoC user function, and we see the sequence. So the first one is x in, the second one is alpha in, and okay. And now we can call start full function, which has three arguments, and these arguments, each of these arguments corresponds to a interface between CPU and FPGA. One means that this particular interface is used within this particular function call, and 0 means that we don't use this interface for this function call. So if we go to full function wrapped.h, we can see the prototype of start full function, and here we see the list of arguments. So vector in required, coefficient in required, and vector out required. So three interfaces, and we set all the arguments equal to 1 because we need all three listed interfaces to perform scalar vector multiplication. Okay, we call this function, we call hardware accelerator. So calling this function is initiates FPGA, so FPGA starts calculations and then returns back the result. And in order to get the result, we wait for calculations to be finished, and after calculations are finished, so we wait inside this while loop. After calculations are finished, we can read data back from a certain predefined area in DDR, from predefined address in DDR. So we call receive vecout function, vecout function, uh, and we provide a pointer to the array where we want to store the result. So we want to store the result of this calculation to the array y1, this one. So we store the result back to this y1 array. So this was all for the first line of the algorithm. And now we perform similar operations for the second line. The only difference is that, so in the beginning we do the same thing. We calculate sine. Now we do this for the second element of the array. So we calculate sine, and then we send only this coefficient, only sine alpha, to DDR, and we don't have to send SoC x in vector because it is the same with the x vector that was used in the first line. So we send only coefficient, and when we call hardware accelerator, we 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 set the first argument equal to 0 because the first interface is not used. So if we come back to full function wrapped, we can see that the first argument corresponds to vec in argument, so vec in interface, sorry. So, and we set it equal to 0 in order to reflect the fact that this particular interface is not involved. So it is already uploaded to FPGA, and we don't want to send the same array again. So we call the function, then we wait for FPGA to finish execution, and then we store the result back, and we store it to the array, uh, and we refer to this array with its pointer. So we store the result back to uh, back to we store the result to the array y2, so which is this one. So we store the result back to array y2. So this is all about writing code. Another thing that we have to do, we have to include math library. So it is already included uh, by Protoip generated template. We have to link this library so that compiler is aware that we are using math library. We need math library because we use sign function, and sign function requires math library. In order to do this, we go to project, properties, C++ general, uh, C++ build, sorry, settings, and here we add into libraries list, we add this library M, which I have already done this. So we add this library M, okay, and we apply this to all configurations just to make sure. So we select all configurations, we add M maths library, and we save the changes. Note that this operation has to be performed when GCC compiler is used. On Windows machine, this is done by default. So this operation of linking the library should be performed only on Linux machines that use GCC. So now we save the project, close it. Okay. We come back to MATLAB environment, and now we call SoC prototype load function again, but keep in mind that now we have already changed the CPU code. Before calling SoC prototype load, I will show you that code in SoC prototype folder. So we go to SoC prototype, source, full user. So the code is changed. So theoretically, we could have changed this code using text editor rather than a Xilinx SDK tool. The only thing why I did it via Xilinx SDK is because we have to link maths library via a graphical interface. But once I have linked this library, I can modify this code directly. And moreover, on Windows machine, as I have mentioned, there is even no need to manually link maths library. Okay, now we have our code ready, and we're ready to call SoC prototype load. So calling SoC prototype load will take FPGA circuit bitstream, will take C code for CPU, will will merge these two parts, and will load FPGA bitstream and compiled C code onto the hardware platform that we use. So now I call SoC prototype load. Okay, SoC prototype load function has finished execution, and we can see the report saying that FPGA UDP TCP server is started and FPGA prototype is ready to be used. And the last step in order to finish prototyping the algorithm is performing hardware in the loop hill test, and we do this by calling SoC prototype test function. So we come to the design flow. Now we call SoC prototype test function that will perform hardware in the loop test and return the results. I call this function. Okay, the test is finished, and if we go to SoC to Protoip project, SoC prototype test results, we have only one project, and you will see the randomly generated input values. Okay, this is input values for alpha, for x, and the results from FPGA for y1 and y2. So if we manually perform calculations, we can verify the fact that they are correct, and so we can just take alpha, calculate sine multiplied by an element in x, and then find corresponding element in y1, and this way we can confirm that the circuit works correctly. Okay. In order to sum up what we have done, we'll refer to this diagram. So on the initial stages of the design flow, we have designed FPGA accelerator, FPGA logic, by modifying foo user CPP function. Okay. After we modified foo user CPP function, we called IP design build command. And IP design build command, what it did, it converted our C code into HDL code. Then we called IP prototype build command. IP prototype build command created Vivado project and converted this HDL code into actual circuit that involves FPGA and CPU. Alright, following this, we modified SoC user file via Xilinx SDK, and this code, as we see, it is responsible for managing the behavior of CPU. Okay, so we have one C file for FPGA, one C file for CPU, and by modifying these two files, we have defined the behavior of the entire system on a chip. And on the final level of the design flow, we have performed hardware in the loop test, where input data is generated randomly within test.hill.m file, and the results are stored back to text file. So one additional thing that we might want to implement is modifying test.hill.m. I will just show you the lines that can be modified without performing actual modifications. So if we go to SoC prototype source test hill, we can find MATLAB code that is responsible for performing hardware in the loop test. Okay, and we see that input data, so SoC X in and SoC alpha in, is generated in a random way. However, depending on the algorithm, user might want to change this. So user might want to change this line, or this line. Okay, and then after generating random data, we have a set of lines that is responsible for calling hardware accelerator, and once calculations are finished, we save data back to text files. So this variable is contains data that came from FPGA for y1, and this variable, this array, is responsible for storing y2. Okay, and that's it. So this is how hardware in the loop test is performed. Okay, thank you for listening.